From when we just left off, we were talking about how, given a power series, we can find two new power series by taking derivatives or integrating from 0 to x. Let's just read this sentence right here. The series obtained by differentiating or integrating a power series will have the same radius of convergence as the original series. However, convergence at the endpoints may change. Okay, well, let's look at example 4. Use a power series representation of 1 over 1 plus x, that very famous geometric series, to derive a new power series representation for 1 over 1 plus x quantity squared. Now, something to talk about, the derivative of 1 all over 1 plus x, well, that's the same thing as taking the derivative of 1 plus x raised to the negative 1 power. That would be negative 1 over 1 plus x quantity squared. Obviously, it's 1 plus x to the negative 2. I just brought that down. But what we're seeing, and we really are going to memorize this if we have not done already, we should. If we have the very famous geometric series 1 all over 1 plus x, recall that that's 1 all over 1 minus x plus x squared minus x cubed. So it's an alternating series, and of course in sigma that would be from n equals 0 to infinity of negative 1 to the n, and then we'd have x to the n, and that would derive the entire series. So if I took that derivative, you can see what would happen. So I'll just say take the derivative. On the left side, we'd get negative 1 all over 1 plus x quantity squared. And here we go again with that term by term derivatives. If the derivative of a constant is 0, the derivative of negative x, well, that would be negative 1 plus a 2x minus 3x squared. We still have an alternating series. Notice that for our sigma, now we lose a term. We no longer start at n equals 0. That constant is gone. But from what we're seeing, just scrolling back up here, you can see that we're going to drop down our n, and we'll have negative 1 to the n, x to the n minus 1. Well, if you'd like to just finish this up and get the proper form, multiply both sides by negative 1, and as you do that, you can see that your negative 1 would get multiplied even inside of sigma. So now this would become negative 1 to the n plus 1. I always go ahead and I double check that the sigma in fact would create the form that I am looking for. It only takes a second to do that, like let n equal 1, let n equal 2, and so forth. But this is a great way to come up with a new series. Similarly, let's go ahead and obtain a power series for natural log of x plus 1. Well, you might guess we're going to take an integral. So again, working with this same series that we had up above, 1 plus x is equal to 1 minus x plus x squared minus x cubed. Say dot dot dot, and we'll even write our sigma here. Sigma can be very helpful. I don't want us to be afraid of it. It's a very useful formula. You know, if you integrate both sides, you're going to wind up with the natural log. You can see how we're working this out in that gray box. Notice that our sigma is still going to begin at n equals 0, just pointing to the top of the screen there. So notice we're also integrating between 0 and x. So what we're really going to do is integrate between 0 and x using a dummy variable. And we introduced that before. So we integrate this left side. We're even going to be integrating sigma as well. Or certainly you could think of it that way. Okay, and we'll just say dot, dot, dot. And of course, this is going to be dx up in here. So we've got our dt. Here's our dt. We'll leave sigma alone just for a moment. We know that as we integrate here, we get the natural log of 1 plus t. But as we would work this out, antiderivative term by term, the antiderivative of 1 would just be a t. This would be t squared all over 2. This would be t cubed all over 3. This would be t to the 4th all over 4. I'll say plus dot dot dot, using the fundamental theorem going from x to 0. Well, we can see what's going to happen, especially on this right side, as we plug in our lower bound of 0. 0 wipes out everything here. We're going to be left with x minus x squared all over 2 plus x cubed all over 3 minus x to the 4th all over 4. Look what happens on this far left side. We'd obviously have natural log of 1 plus x minus, when we plug in 0, 1 plus 0 is 1, natural log of 1 is just 0 itself. So notice what we've done. We've come up with this power series representation. You might wonder what's happening in regard to sigma. Well, my goodness, if you were to just even integrate sigma itself, wow, look at this. We'd get x to the n plus 1. We're going to divide by n plus 1 in so doing. We'll have negative 1 to the n. Very, very quickly, let's just reconfirm by checking term by term that this is, in fact, what we're arriving at. Indeed, we are. Real quickly, to save us some time, for example 6, calculate natural log of 1.2 to 4 decimal places. Well, guess what? We're going to use this series up above, but we're going to let x equal 0.2. So the natural log of 1.2 is going to equal 0.2 minus 0.2 squared all over 2 plus 0.2 cubed all over 3 minus 0.2 to the 4th all over 4, and we're going to keep going. All of a sudden, this might look a little bit more familiar from what we were doing just a little while ago, especially on this right-hand side. 4 decimal place accuracy. Well, this is an alternating series. Wow. Just as before, we know that up above we knew that we'd be having this series for x less than 1 in absolute value. It's still true. We would have to address endpoints, but we're not even getting into that at this moment. But just cutting to the chase, helping us out a little bit in regards to time, what we can definitely see is if we went out to the 6th term, 0.2, or let n equal 6, divide by 6, that would be the first time that we would be accurate to 4 decimal places, because we know that our error must be less than this 0.00005. The first term that we see doing this is 0.2 raised to the 6 all over 6. So what does that mean? It means we're going to actually add up to n equals 5. So we're going to say find s sub 5. So in so doing, if we said this is 0.2 minus 0.2 squared plus 0.2 cubed all over 3 minus 0.2 to the 4th all over 4 plus 0.2 to the 5th all over 5. Use your calculator. Hopefully you will confirm what I am seeing right here, 0.1823. That's your sum accurate to 4 decimal places. Real quickly, let's take a look at example 7. Find a power series representation for arctangent. Wow, sometimes we look at this one and think, where do we begin? Here's where we begin. We'll look at 1 all over 1 plus x. This is 1 minus x plus x squared minus x cubed. And of course, this is in regard to sigma. We know that we go from n equals 0 to infinity, negative 1 to the n of x to the n. Well, tell you what, if I wanted to find 1 all over 1 plus x squared, well then everywhere where I have an x, I'm going to replace it with x squared. And we've done something like that before. By the way, this would even occur inside of the sigma. And again, just really making this clear, I hope. Everywhere where I see an x, I could even envision that there are little parentheses around there. So whatever I am substituting in place for x, I have to plug into those parentheses. And let's see what we'd be left with. This is 1 plus x squared equals 1 minus x squared plus x to the 4th minus x to the 6th. This is going to be negative 1 to the n, x to the 2n. So n equals 0 to infinity. Well, if I want to find arctangent, let's recall something. This can be so helpful. 1 all over 1 plus x squared dx is equal to arctangent of x plus a constant. Wow. So what we'll do real quickly is integrate from 0 up to x and throw in that dummy variable again. We're going to integrate on this side as well. Again, throwing in that dummy variable. Again, I hope you understand where we're going with this. We are doing something just amazing. We're doing a term-by-term integration. The integral of 1 with respect to t is just a t. This is t over 3 all over 3, t to the 3rd over 3, plus t to the 5th all over 5, minus t to the 7th all over 7, and so forth. But fundamental theorem will go between x and 0. Here, as we said before, we'll have arctangent of t evaluated between x and 0. So look where we're headed with this. The left side of this equation, just cutting to the chase, fundamental theorem, arctangent of 0 is 0. So we could just say, well, look, this is the arctangent of x. Thankfully, this lower bound of 0, when we plug it in, my goodness, we are going to see all of those terms collapse to 0. And, wow, very, very powerfully, we can also see that this has really affected sigma as well. If we're really on our toes, we're going to know that what has just happened is integrating just sigma. We'd have negative 1 to the n. Look, bump up your power. This now becomes x to the 2n plus 1. Divide by 2n plus 1. Notice we still start at 0. If we take a derivative, then we start at 1 then. But my goodness, we're almost done. We just should double check this super quickly. Sure enough, this would work out term by term. Notice that 2n plus 1 actually is odd, isn't it? So this, thankfully, is our series. Well, my goodness, for our last problem, we'll very, very, very quickly do that in just a moment. We'll have to have a brief part 3.